Okay, welcome back, everybody. Hope everyone had a good week. We got a couple announcements, a couple of things to go over. Let me get organized here real quick. Shut off my phone. Okay. I'm looking through the schedule of what we got left. We basically have 6 time periods on Friday to meet again. So I split that up. We are on chapter 11. We got, up to chapter 16. They're fairly short chapters, not very long. And so what I decided to do is make a schedule both for this class and my GCC class, okay? So let's take a look at what we got going on first. All right, so today is the 1st. Happy April Fool's Day. The blue is SCC, my yellow is the GCC class, okay? All right, so today we will go over chapter 11 and then jump into 12 a little bit. I want to adjust that. And then depending on how 12 goes along, we may continue through 12, 11 and 12, because 11 is extremely short, very short chapter. And 11 would take a little more time. And then I'm going to open up the remaining time for 1 or 2 things. Is one, we can go over, which I'm going to be doing on Fridays, is go over the worksheets associated with that chapter. Okay, to help to go over the problems. And then we'll continue that until the next week. We'll continue possibly on 12 and or 13. We may need to shift it up a little bit. And then once that chapter is done, then we'll go into the worksheets or open it up to questions. The advantage of this is we'll be finished with that chapters 10 through 12 way before the 16th. Okay, which will give you plenty of time to prepare for it. We got 2 more exams left. On the 16th is exam number 4, which covers chapters 10 and 12. Okay, so that would also, given the number of chapters we got left and saving some time at the end of the lecture part, I'm going to stay here until my allocated time of 2:40. It would open up for any questions you may have for that particular chapter we just got done with, or any chapter that you want to talk about and go over problems, okay? So you may start looking into that and coming in, you thinking with a mindset that at the end, I'm ready with some questions if you have them, okay? And so we'll continue with that for every Friday with that aspect. We'll do a chapter. The rest of the time, we'll do the worksheets and or any other worksheet, the worksheet for that chapter, or any other questions you may have concerning whatever chapter we covered. And I state that because the final exam is a comprehensive, I repeat, okay? As I stated way back in the beginning of the semester, it is a comprehensive exam. It will cover all the, not all, it will cover chapters 1 through 15. There will not be chapter 16 on the final, okay? Simply because by the time we get done with it, I don't think you have enough time to really prepare for it. So only chapters 1 through 15. However, chapter 16 does have homework associated with it, okay? So that brings us to May. Now, the 13th is the final exam. That's the schedule for the final exam. Notice that it's not on Saturday like the other exams. It is on Friday, okay? The last official school day for SCC. Actually, it's the 12th, but they tend to forget about the Friday classes, but that's okay. On the 13th is also the last day to do, if you want, any of the homework assignments or any assignments which were not completed. You didn't do them, or they're, you can go back and knock them out, because all those are open. All the labs, all the homework is open until the 13th, but be aware that they are open, but they do have a penalty of points associated with them. which brings me to a point. For the homeworks, there are 2 attempts, okay? Now, what some people have done in the past is just do 1 attempt and they're happy with that grade and then move on. Now, if you're not happy with that grade, and let's say you want to go back and do the 2nd attempt for any of the old homeworks, what happens is, and maybe you got a better score on that and you want to keep that score, well, Canvas thinks that 2nd attempt is late and puts a penalty on it. If that happens to you, let me know and I'll take off that penalty for you. Okay, I repeat, this is for the 2nd attempts, for only for those homeworks that were turned in on time originally. Okay, if you go back and do the 2nd attempt because you want to improve the grade, and you will get penalized for it, but no problem, I will take that penalty off. Okay, if it's late to begin with, I can't do that. It was late to begin with. It has this penalty associated with it. Let's see what else. Yes, the nomenclature exam. You may notice that your grades probably dropped a little bit. And I explained that during our introduction in first semester, and I explained it again in the email, is in the past semesters, I would wait. Yes, I know the nomenclature exam does not have a due date until May. But what was happening was this. A lot of people waited until the last week or so in May before they attempted it. And as per SCC chemistry department policy, you have to score at least an 80% to keep that 80%. Anything less than 80% gets dropped back to 0. And so what was happening once the students attempted it 1 or 2 weeks at the end of the semester, for some reason, they couldn't get that 80% mark and they tried and tried. Now for them, they were on the border. So that 10% overall for that nomenclature really pushed them off that border. In other words, prevented them from getting, let's say, a C, and it kicked them into the D range. And they didn't really have enough time left over to continuously try and try till they get to 80%. So to deviate that, I do that like I put a 0 in there about a month or so before the end of the semester so you can see what your actual grade is without that nomenclature exam, okay? So that way you also remind you that, okay, if it doesn't affect you and you're in the middle grade and, and you're happy with it, that's fine. It's up to you, it's your choice. But what it can happen is 1 or 2 things. It can put you, let's say you're in the B border, upper B, and without that nomenclature points, you can get kicked up to the A. So that's what's keeping you from getting into the A. On the same token, if you're down, at the other end of the spectrum, let's say you're at the C, and that 10% kicks you into the D or less, but it kicks you into D, it prevents you from staying in the C range. So, that decision to take that exam, totally up to you. But I want to show you where the grade is. Actually, because Canvas doesn't calculate your grade. It only doesn't calculate your grade until everything's been graded. So I'm still in the process of adding more updates, and you'll see that your grade will go up, especially when the labs kick in, and most of you, by and large, do very well in the labs, so that will kick you up to where you were originally, as I input the grades for that. So any questions about that, about the nomenclature? I know some people don't like that 0 in there, but I'd rather have it done early so you have an idea of what's going on rather than wait until the 13th and then, because on the 13th, Canvas shuts off. You can't access anything, okay? All right. So we'll probably meet. I will be here on the 13th for about an hour or so. The 13th, we're going to be done with all the chapters. There will be no Zoom. But I normally come in anyway for about an hour in case there's any questions with respect to the final exam or any of the topics, and we can, help you out that way. If after about an hour, this is on the 13th, nobody shows up, I just shut it down, okay? All right. That weekend, I spend time tallying up the final grades. I will send an email out to you and say, okay, everything on my end looks good. I will submit the official grades sometime, maybe Sunday, because I got to get them in by Monday, on the 16th. So I'll let you know beforehand before I submit the original, the final official grade, so you can make sure that it corresponds to what you see from your end, okay? The other aspect, some of you may want to, or may be thinking, okay, I think I want to drop this class. And, you know, it's totally up to you. I have the ability to drop you once you pass the timeline where you can't drop yourself. And if that's what you want to do, please send me an email through Canvas that is what you want to do. And also, I can't drop you after you take the final exam. If you take the final exam, you're in. I got to submit whatever grade you got. But if you're thinking about it, I don't think anyone here is in the danger of getting an F. But if, for whatever reason, I've had a variety of reasons why people want to drop, you can't take the final exam, okay? And then take, you know, it's not like I can take the final exam, then request the final. I can't do that. Okay, any questions about what I just said? Okay, so there's no confusion. I did have an email from, I forget what department, concerning those 2 days that we did back in February, that those 2 Fridays. I understand some of you were not happy with, but I got to remind you that even originally those 2 days we were not going to meet, but I changed that and we did meet. I did record all the lecture, so you can access it. And some of you are looking at them, looking at the recording, but not all of you. So, you know, I'm doing everything I can from my end, given the online environment, to make sure you succeed in this class. So if you ever have any questions or concerns, my door is wide open. Send me an email. We can set up a Zoom if you need extra time. Some kind, you can't go to tutoring. I can do tutoring here to Zoom. Send me an email. We can set up times. Also, you'll see here in this calendar, the yellow. Well, that's for the GCC. My GCC course. You are more than welcome to come to those days. I meet between 3 and 4:15 for the GCC class. Same link for the Zoom. So you're welcome to jump in. I tell the GCC students they're welcome to come into this class. So, you know, feel free. All right. Any questions? Now, you do have 2 sets of videos, the videos that I record here for this lecture. You also have the set of videos that are pre-recorded by Dr. Kim from GCC concerning the topic. So you do have access to a lot of resources to help you through this topic. You also have, obviously, tutoring at SCC, excuse me. And you have me here if you need anything. My door is open. It's always been open. My job here is to help you succeed with your coursework, with this coursework, okay? All right, any questions? Comments, concerns, feel free to jump right in.
So could I complete the nomenclature exam next week?
You know, if the nomenclature exam, as you reach that 80% mark, you're done. You don't have to go any further.
So it's unlimited attempts, right?
Pardon me?
It's unlimited attempts, correct?
Yes, unlimited
Okay.
attempts. I've had people that tried, 40, 50 times, and that's fine. I've had people who got the 80% and then say, no, I'm going to try for 90, and they continue.
Okay.
It's set up so it will keep the highest grade.
Okay, thank you.
Yeah, no problem. I do go into the nomenclature exam once you complete something, and I look at it because there are some questions which we're still teaching Canvas to recognize as correct. And so I go in there and I check to make sure that your answers have been marked correctly. Because Canvas, I may have mentioned this before, if you add a space in Canvas in one of your answers, Canvas, thinks it counts all the characters. And if the answers if the answer has 5 characters, for example, and you add a space, Now it's got 6 characters, and Canvas treats it as incorrect and marks it off. So I go in there and check all the answers to make sure you got the points. There were some corrections for the last lab that Canvas, for some reason, when it got copied over, did not carry over something correct. So I've been going in there correcting it and giving you credit for those questions. So anyway, any other questions? Canvas is not, definitely not AI technology. It's a pretty good program. I've worked with other ones. Not too bad. All right. Well, I'll tell you what, let's continue with chapter 11 then. Very short chapter. Okay. Now, this particular chapter deals with, let me close up my stuff here. Bear with me for a second. Okay. All right, this chapter deals with a topic called thermodynamics. This is an area in chemistry. And if you look at the words used to describe thermal and dynamics, well, thermal obviously deals with heat. Heat is associated with energy. Normally, when you put energy into the system, it causes the heat to heat up the system. There's a temperature rise there, or it could be a temperature decrease, depends on the system. And dynamics deals with how your system interacts with each other and how it interacts with the environment. Now, this particular topic or discipline, we are giving you like the tip of the iceberg. It's a whole discipline in itself. Very fascinating for some aspects, but it also can be very boring. But that's my personal point of view. It's thermodynamics. But anyway, we tend to think that reactions, we simply just put reactants together and magically we got some Harry Potter thing happens and magically you got a product. I wish it was that simple. There's a lot of things that need to come together to get a reaction to go from point A to point B, okay? And for example, we have this reaction where we're having 2 diatomic molecules coming together. Okay, so we see the 2 diatomic molecules coming together. Let me change the color here. And this one here and this one here. And then eventually we're going to make 2 new products of some sort. Okay. Of a yellow and a yellow-blue combination, we're making some compound. Obviously, so we're taking 2 elements and creating some type of compound. But to get from point A to point B, they go through this intermediate, okay? And we call that TS, that stands for the transition state. It is a point in time where we are breaking bonds right here, this original bonds being broken, and then we are creating new bonds, okay, right here. And so it's a hybrid of what it looks like for reactant side, and then there's what it looks like for the product side, okay? So this transition state's very quick, at least it's theorized, very quick. Some transition states hang out a little longer, but the point here is this: reactants go through a transition state to form products. Second aspect about this is that this requires an X amount, a very specific amount of energy, which I'm going to denote as E, okay, energy, a specific amount to activate the reactants to go to products. Hence, that energy has the subscript ACT, which is then described as the activation, energy of activation energy that is necessary for the reactants to go from reactant to product via the transition state. Very specific amount. If we don't have enough, that specific amount of energy, we won't get across this hill. It's basically a hill we're gonna pass, this barrier to get down to the other side, you know. And for example, I equate that to climbing a big mountain. You know, that mountain's gonna require an X amount of energy, your energy, to get up to the top of that hill. If you don't have that energy, enough of the energy, you're not gonna make it up there, okay? Now, the other aspect you can see from this diagram is, let me clean it up a little bit here. If we look at the reactants, they have very specific orientation. Notice that? And so they have to orientate themselves with a specific amount of orientation. Otherwise, the reactants won't come together just right to form products. And so you can hopefully see here that some of the factors involved with the reaction are they're going to have specific amount of energy, right, to overcome. So then not only on top of that, they're going to have a specific amount of orientation. I equate this to shooting pool. Anybody ever shoot pool, or maybe billiards or whatever, same thing. You got a ball, you got a cue ball. Okay, you're trying to make that ball, let's say, to the corner pocket. Either going to go a direct hit or you're going to bank it off. You have to hit that ball, that cue ball, with the right amount of energy, okay, so that the ball you hit gets to the pocket you're aiming for, right? I'm sure if you shot pool and you hit it with enough energy, that ball just maybe trickles down there, doesn't make it. That's one aspect. The other aspect is, you have to have the right angle. You got to hit that cue ball with the right amount of energy and the right angle so you can shoot that whatever ball you're shooting at, trying to get to the corner pocket. If you don't angle it right, you don't hit the corner pocket. You don't get enough energy, enough hit, you don't make the corner pocket, okay? And so I equate that, like I said, to shooting pool when we talk about chemical reactions coming together. All right, so that's the transition state that we talk about, and that's that intermediate between reactants and products. Okay, so we can assure that we get sufficient reaction by getting more collisions. That increases the chance of enough energy and enough orientation, right? So we can do a couple of things to increase the number of collisions. The simple thing to do is to heat the reaction up. If we heat that reaction up, the molecules are excited and then they start moving a little faster. That increases the probability of them reacting with whatever they're going to react with the right amount of energy and the right amount of orientation to get you a product. Okay, but you got to be careful with it, because sometimes if you heat it too much, you actually cause the reactants to decompose. So it's like a balancing act here. I once had a reaction I tried to work. It looked good on paper, but it took me a couple of weeks to finally get that thing to work properly, because it was very temperature sensitive. Too much heat broke it down. Not enough heat did not get the reaction to proceed. Okay, so we need enough energy of activation, as I stated. We need to increase the collisions, and we have to make sure these molecules are orientated correctly. Okay, so we have what's called the rate of the reaction. That is the speed that the reaction proceeds. Okay, we can increase the concentration. That's what they're saying here. We call that this bracket here represents a concentration factor. Okay, we can increase the concentration. Makes sense, doesn't it? If I increase the concentration, I get more chance of reactants coming together to form a product. I equate that to, let's say you're a room, I don't know, 10 by 10 room, and I got just two people in there, and they're walking around aimlessly. Okay, you get those two people walking around, well, there's going to be some point in time where they may be walking to each other, all right? With just two people, but the probability of that happening is low. They can, the probability of it occurring is possible. But as they walk around in their little 10 by 10 room, you know, they're far apart, there's plenty of room. Now throw in about 50 people in that room, all right? Now, the probability of two people coming, walking around aimlessly and bumping into each other is increased, right? Because you've got more people in there. The other aspect, you can also decrease that room from a 5 by 5, 10 by 10 to maybe 5 by 5. Now you decrease the area, and now whatever concentration you have, then you increase the probability of reactants to come in together and increase the probability of getting product. Okay, so you can increase the concentration, adding more people, which results in more reactants, more collisions. We can increase the temperature, as I stated. Molecules move faster, more collisions occur simply because more energy, but you got to be careful because too much energy can cause the reactants to decompose, and or the product that you make could be heat sensitive. And so even though, yeah, you're getting reactions to occur, but because of the temperature factor of the reactants, they break down and you don't have the product that you're searching for, okay? We can add what's called a catalyst. Okay, a catalyst is simply a material that actually aids in the reaction. What it's doing is it's actually lowering the energy of activation necessary for that reaction to proceed. So instead of having, let's say, 50 units of energy for this reaction to proceed on its own, by adding a catalyst, it may bring down that energy requirement down to maybe 10 units of energy. And so the reaction that at one point maybe required 100 degrees Celsius temperature to occur could now occur maybe at room temperature, and there's enough energy at room temperature for this reaction to proceed. And you got to be careful. Now, the catalyst, all that does is, and it doesn't interact, does not become part of the reactants or the products. It just helps that reaction to go on. And then itself, once it's done, it goes on and helps some more reaction to occur. But you got to be careful because some reactants, some catalysts can get the reaction to go out of whack. I had a reaction one time where my job was to make the two reactants, separate them and put them into sealed tubes, put these sealed tubes into a heated bath, and then take them out in periodic times, at known times, take a tube out and then analyze the tube for the reaction products and reactants, and do that over time. Well, something happened. We found out later on that what it was, I had a trace amount of iron in my solution, and that acted as a catalyst. And it made the reaction proceed, but it made it proceed very fast. The result was, as I put my tubes into the heated bath and I stepped away from the hood, I put everything in the hood. The moment I stepped away, the whole thing went kaput. It was a lively reaction. So catalysts, like I said, they're very functional. Our body is loaded with catalysts. There's reactions that if without the catalyst, they may react, but it may take years. And good thing for catalysts that we have, because a lot of reactions, I'm surprised that we even exist as we exist, because some of these reactions are pretty complicated, and the catalyst there is very important to assuring that you are able to function and have life as we define as life, human life, because of the catalyst. Without it, it would be a little bit different. All right, so as I stated, the energy of activation is the minimum amount of energy needed to react. That is to turn reactants to products, okay? We also have equilibrium reactions, and we introduced this concept when we were talking about weak acids and weak bases. we showed a reaction. Normally, if it was a strong acid, strong base, it dissociated 100%, and we had a reaction error that was only one way. But we had some examples of the weak examples where we had two reactions, where we had a forward arrow and a backward arrow or reverse arrow. And that's simply just telling you that there's an equilibrium. We have both reactants and products. And the rate in the forward direction equals the rate in the backward direction or reverse direction. And we reach an equilibrium, okay? A good example, which is not really a true reaction, but it's a process. If you take a soda bottle, okay, capped, shake it up. What happens? You see those bubbles come up, right there, carbon dioxide. Before you shake it up, carbon dioxide is in equilibrium in solution, okay? Now, the moment you shake it up, that pressure, that carbon dioxide comes out of solution, you build up pressure. Now, if you leave that bottle alone and you let it sit there, what happens? The pressure goes back down. You go back to that state of equilibrium, wherever it was to begin with, and now you can open that bottle, okay? Because if you open it while it's still bubbling, you can have a big mess. All right, so equilibrium is defined as the point of reaction reaches when the rate of the forward reaction equals the rate of the reverse reaction. All right. Now we're going to talk about energy profiles, and what I'm going to do here kind of define it. Now, what we do, the way what an energy profile is really basically is a graph. That's all it is. It's a graph describing a reaction process, and we got the x coordinate, x-axis, and the y-axis. Okay, the y-axis we have units of energy, and we're going to just use generic units, just units of energy. And obviously, being a graph, we can plot this out, put our scale and say, I don't know, 10 units, 20 units, 30 units, 40 units, 50, 60, 70, and 80, okay? Now, on the x-axis, we call that the reaction coordinate, meaning basically we get a reaction to proceed, and then we take a snapshot of it, okay? And then at that snapshot, at that moment in time, we have an estimate of what the energies involved with that reaction. And then we later proceed, and then someplace else we take another snapshot and another snapshot. And so in essence, we have data points, okay? And so by taking all these snapshots along the coordinate, the way the reaction proceeds, we can actually plot a graph to describe this reaction. Now, in the beginning, our reactants are sitting at some reaction level. Okay, so I'm going to label this spot R. Oh, you know what? Let me redo that. Let me move up a little bit. Okay, let's start at 30. Okay, so R represents where our reactants began. And if we look at the energy, we just extrapolate across the graph, that's about 30 units of energy, okay, to begin with, okay? So these are reactants. All right, so we put the reactants together, and then the process reaction proceeds, and we start collecting data, and then we just connect the points, and we end up with a graph that may look something like this, until such point where we're on the other side here, where P represents the products, all right? And if you take and you extrapolate, I can't really do a straight line here, but if we extrapolate across to the axis, guess what? We're about 10 units of energy, okay? Now, on top of the hill, that is where we believe the transition state exists. That is, we denote that by TS. That is our transition state. That is that point where you're getting both bond breakage and bond formation to make whatever the product you're making. Now, if we extrapolate where the reactant started off with, at 30 units. Okay, we extrapolate with a dotted line, and we go up to the point where the transition state is, and let's say we extrapolate across another dotted line, and we see that transition state is at roughly 70 units of energy. Okay. Now, when we talk about the difference of anything in science, we're talking about delta. We use the symbol delta. And in general terms, delta is simply the change of whatever you want it to be. So the change of energy here is always where the energy, let me put it this way. The delta is where you ended up with minus where you started off. And it could be temperature, it could be energy. That's why I put it in general terms. So the change of anything is where you ended up minus where you started. And so if we look at the change of energy for where we ended up at 70, that's the transition state, and we started off at 30, minus 30, E, okay, that means that is 40 energy units between where the reactants, where the transition state is, and where the reactants began. So that's 40 units of energy, okay? That area is called the energy of activation. For this hypothetical reaction, the energy of activation is simply 40 units of energy. That's how much energy I need to get on top of the hill. If I don't have 40 units of energy in this example, if I got 39, I never hit that reaction, the transition state, and I don't have a reaction, okay? All right, so that's the energy of activation. It's the change of energy between the transition state and the reactants. Now, another area is where the reactants started and where the products ended up. Okay? And that has a very specific symbol. It's called delta H. That is the energy of the reaction. And like I said, any delta is where you ended up. Well, we ended up at 10 energy units for the reactant products. And we started off at 30 for the reactants, right? And so it's 10E minus 30E, which gives us negative 20 energy units. The key is this. The fact that we got a negative value tells us some important bit of information. That tells us that this reaction, the way it was written, the fact that the energy level of the products is lower, ended up at a lower energy level than the reactants, giving us a negative value for delta H, tells us that we have what's called an exothermic reaction. Exothermic, meaning that it gave off heat. It got hot. Remember we introduced the exothermic reaction and endothermic a while back? Okay, so in this case, we end up with a negative energy unit value and exothermic. And a good example of this would be you go to the pharmacy and you buy a hot pack. You injure your muscles, doctor says put a hot pack on it. Get the hot pack, you crush up the ingredients, there's a reaction that proceeds. It's an exothermic reaction and heat's given off, and then you can put that pack on wherever you injure yourself. And the same token, the converse of that is this. There are cold packs, okay, where you mix up the material, and then what happens is energy is sucked into the system, and it gets cold, okay? So energy is a reactant there, and it needs energy from the environment, and so pulse from the environment resulted in a cold material. Here, when it's negative, energy is a product, so it gives off heat, okay? All right, so this is where the main points, and that's why you see in that graph on top, I tried to explain what each one meant, okay? Be familiar with where the reactants are, be familiar with the transition state, where that is at, be familiar where the energy of activation is and how it's determined. Okay, and be familiar where delta H is right here. That's the difference between the product minus the product energy level minus the reactant energy level. Okay, and this is the typical example of an exothermic reaction. And if you look at the graph here, notice that the product energy level ends up at a lower energy level than the reactants. Okay, and that indicates to you that you're going to end up with a negative delta H. Okay, I put values on the axis so you can see the actual values. Okay, you got a negative 20. See how it is done, see how it's calculated mathematically, okay, with some relative numbers in to give you a perspective there. All right, well, let me clear this up a little bit. And transition state, that's what we talked about. Delta H is the change in heat energy, that's the energy of the reaction, which, as I stated, is the energy of the products. Now, the term here, they use heat, but we interchange the word. Heat and energy, they're related, because if you put heat into the system, guess what? Energy goes up. You take heat out of the system, guess what? Energy drops. Okay, so it is the product's heat. I prefer the word energy, but we'll go with the book. Delta H is the change of heat energy, which is the product's heat / energy minus the reactant's heat. Now, when it's an endothermic reaction, okay, that means that heat / energy is a reactant, and it's to the left of the arrow, is written here. So you got reactants plus heat equals products, or gives you products. Furthermore, it enters and heat / energy enters the reaction. So this reaction, endothermic, would get cold. The container would get cold. The converse of that is an exothermic reaction, where reactants lose or release heat energy, and that means that the heat / energy is a product. So heat exits the reaction, and it is to the right of the reaction area, okay? And it gets a little warm. Okay. In this case here, you're given a graph with all the major units there, where the reactants are, the transition state, energy of activation, delta H, and products. And they're asking you here, is this an exothermic? Is delta H negative or positive? Well, again, notice that, yeah, you can arbitrarily put some numbers in there so you can see that mathematically. You can say 10, 20, 30. And so it is delta H is products, which is 10 units minus, say, 30 units. And it's 10 minus 30, and that is a negative 20. Okay, negative 20. Okay, and so that tells you that you have a negative value, which, again, having a negative value tells you it's exothermic. Okay, so you can do it mathematically, or you can do it visually and recognize that the product's energy level is at a lower energy value than the reactants were when they began, the reactants, that is. And so when you subtract that, you're going to always end up with a negative number. Okay. All right. So here, as I mentioned, be able to draw the transition state, the delta H, reactants, products, energy of activation. Now notice the difference in this graph, okay, compared to the previous one we just did, exothermic. Now, in this case, you might say, whoa, let's take a look at this. Well, let's just extrapolate. Let's go over here all the way across and reactants, and then let's say we, again, 10, 20 arbitrary units, 10, 20, 40, right? So delta H is the product energy level, which will be about 40, minus the reactant energy level, which will be about 10. And so that means the delta H is about 30 units of energy, okay? 30 units of energy. Guess what? It's a positive value, okay? It's a positive value. So delta H being positive should indicate to you that this energy profile is a description of an endothermic reaction. Okay, endothermic reaction, because we have a positive delta H. Therefore, being endothermic, it will get cold because it's taking energy from the environment into the system. Okay, and so you can do that mathematically like I just demonstrated, or visually by seeing that the product energy level ends up at a higher energy level than the reactants were, okay? Which will result in delta H being a positive number. Okay, so this one here, this be a positive delta H. Okay. Again, because the product's final energy level, it is a much higher level than the reactants. And the delta for anything is the difference between where you ended up minus where you started, okay? You can see here visually the two different graphs. The top one is an exothermic reaction. And so delta H would have a negative value. And here, the bottom one, delta H, will have a positive value, okay? Again, because so this means this is exothermic for the top, endothermic for the bottom one, okay? And again, for the exothermic, the product's energy level is at a lower energy state than the reactants were when they started off. And the reverse for an endothermic, where the product's final energy level is at a higher energy level than the reactants were for that reaction, okay? All right, well, I mentioned before that catalysts are very crucial for a lot of processes, not only in the chemical industry, but in our body industry, if you will. There's a lot of reactions that occur in our body that without catalysts, they just wouldn't. And they function in different ways. A lot of times what they do is these catalysts are pretty big. And what they do is they offer a position so reactants come together in the right orientation so that reaction can proceed, okay? Then once they're done, the reactants are let go and the catalyst goes on to do the same thing for another pair, another set. But in essence, what a catalyst is doing is just simply lowering the energy of activation. So, you know, if I take a look at the energy of activation here for a normal reaction, you can see visually that it's much higher than the energy of activation with a catalyst. And so this reaction, say the one that's normal, which sometimes may require a little bit of heat to warm things up to get to past that energy of activation, for that reaction to proceed, you can see here when with a catalyst, that reaction does not require a lot of energy and could possibly occur at room temperature, okay? Room temperature. Okay. So, guess what, ladies and gentlemen? I told you it was short. It was short. Tell you what, let's take a quick short break. I need to run a quick errand here in the house. So let's come back at 1 o'clock. I got 12:40. Hey, I took a look at the nomenclature bonus, and Lisa, thank you for, it was you, Lisa, right, who asked the question. There is a typo. Surprising. Anyway, let me share it with you. Nomenclature exam on the syllabus, it says the week of the 4th, but that's not right. I mean, we don't even come near the nomenclature chapter in the fourth week. It should read the week of the 11th. Okay, by the 11th week. If you do it before the 11th week, which is next Friday, actually, this is the 10th week, I believe. Let me double check. And so those of you who have completed that already at the 80%, I will go back in there and give you your 1%. Okay, so yes, go ahead.
So we still have till the end of next week then to get the extra credit?
That's correct. That is
Okay,
correct.
awesome. Thank you.
Yeah, that was a big typo. That should read 11. Don't know what happened there. All right, so yeah, I'm looking at the calendar. Today is the 10th. 11th will be the 8th. Okay, and I'll extend it to the following Monday, so that'll give you that weekend to work on it. So what that does is at the maximum, you'll get whatever points out of 20 you get. Let's say you get 16 out of 20. Okay, well, let me correct this. Make sure you got to get your 80% first. That means you passed it, okay? It doesn't mean, so at the 80% mark, then we add a 1% on top of that, okay? All right, so if you got like 18 out of 20, then that kicks up to 20 out of 20. Excuse me. All right, so you're at 16 out
Thank you.
Out of 20, then that kicks you up to 18 out of 20. Okay, just adds 2 more points to the amounts you get. Okay, any questions about that? Good thing. I gotta make note of that. All right, any other questions? Good.
Thank you.
All right, quite welcome. All right, well, I tell you, no questions. Let me jump into the mole because there's no worksheet for the energy one. The energy one, just look at the graphs I just showed. I'll be able to determine, those points as far as where the products are, where the reactants are, where's the transition state, where's the energy of activation, where's delta H, okay? Maybe determined by looking at the graph, is it an exothermic reaction or an endothermic reaction? And if so, is the value of delta H negative or is it positive? Okay. Like I said, we're just talking just the tip of the iceberg of thermodynamics, which is a fascinating field in itself. There's an area called a measure of disorder or the entropy. Nature wants to go to a state of disorder, like my desk here. All right, so we're going to jump into the mole. The mole, which at first time I saw this in the first chemistry class, I saw this and I said, mole, we're going to talk about mole. No, we're not. We're not going to talk about mole. Okay, so this is an important concept, the mole, because in order to be able to correlate going from compound A to compound B with respect to calculations. Now recall what we've done so far up to date. We started with the elements, okay? And then from the elements, we were able to get the ions, we put them together in compounds and molecules of compounds, and then we start to react them with each other. We had 6 types of reactions that we talked about, okay? Then from that point, we also talked about balancing those reactions, making sure we have sufficient amount of atoms for reactants and products, okay? And then from balancing those reactions, we put coefficients in front of the formulas. That tells us the ratio between reactants and products. And that is what we're going to utilize to be able to go from point A to point B with respect to a chemical reaction. Okay. So for example, and I'm going to give you a hypothetical example. Let's say we got A plus B gives us, I don't know, AB. And after we balance it, we find out we got 2 of these, maybe 3 of ABs, and maybe 4 of A's, for whatever they are. Okay, those coefficients balance this reaction. Those coefficients also tells us the relationship between reactants, meaning here, I stated that tells me that I need 4 A's for every 2 B's, okay? And with respect to the A's, the relationship between the A's is a 4-to-3. So when I start with 4 A's and sufficient amount of B, I'm gonna make 3 ABs, okay? And the same relationship similar between B and AB, which is a 2-to-3. That relationship is very important, okay? Because that's gonna allow us now to say, I don't know, let's say, for example, we start off with 10 grams of A. I need to calculate now, how many grams of AB will I make? Now, I cannot go directly from grams to grams, okay? If I knew how many grams of A and how many grams of B, I could calculate how many grams of AB I'll make, because the conservation of matter tells me if I start up with the total amount of weight of A and B, I should get the same weight with AB. But I don't know that. I'm just given the amount of A. And in order to calculate how much AB I need to make, I need to go through moles, okay? If I start with grams, I need to convert the units of grams into moles of A. And once I do that, now I can compare apples to oranges. Right now, without that concept of moles, I can't compare apples to oranges. But once I convert the A's to moles, and then I use the relationship from the balanced chemical reaction of A to AB, which is 4-to-3, and I set that up in the ratio, now I can get to moles of AB, okay? And once I know moles of AB, I can go to the next step and calculate grams of AB, okay? Now, so this mole concept is very important with respect to our calculations. But it poses a challenge sometimes with students, because it just does. And I try to pick an analogy, and I try to use as many analogies as possible, because there's a lot of things out here in quote real life that we can use to help us understand some of these concepts. And the concept of the mole, its analogy I'm going to utilize is a dozen. Okay, a dozen, because we know that in 1 dozen there are 12 units of something, right? Of course, we equate it with a dozen eggs. We know there's 12 eggs. And when I say to you, okay, I got half a dozen eggs, well, it's half of that, 6. And a 1/4 dozen of eggs, we got 4, et cetera, okay? And so the mole is nothing more than a count. It just happens to be a very large number, very, very large number. Specifically, it is a number that's 6.02 times 10 to the 23rd units. And I say units because it's a count, just like a dozen. I could have a dozen eggs, a dozen donuts, a dozen whatever. It's a unit of count, right? And so the mole is nothing more than a unit of count. It just happens to have a very big number. Remember this, take that decimal point, move it over 23 times. That gives you an idea how big this number is. And I say units because units could be 6.02 times 10 to the 23rd donuts, or guess what? It could be atoms. Okay, it could be ions. Okay, it could be bananas, oranges, it could be whatever. Okay, we're going to be using obviously atoms and molecules and compounds. Okay, but it just happens to be a big number. Okay, so that is the mole. Now, let me get to the periodic table. On the periodic table, okay, we talked about this, may have, maybe not, but yeah, we did talk about that number below the symbol. For example, in carbon, that number 12.01, that was the atomic weight of carbon. And remember, we did talk about when we were talking about isotopes, that number is not a whole number. We have the different isotopes. We talked about carbon 11, carbon 12, carbon 13, carbon 14, okay? And those are whole numbers because that is a sum of how many protons, how many neutrons this carbon had. The electrons were weightless for all intents and purposes and didn't really count with respect to the weight. The protons and neutrons each had a atomic mass unit of 1. All right, so carbon 12 had 12 protons, 12 neutrons. 11 had less neutrons, etc. These were whole numbers. And what is done is all these 4 isotopes, the numbers are average. So if I take the number 11, 12, 13, and 14, and I just straightforward average them, remember I get 12 and a half, right? Take the sum of all those numbers divided by 4, I should get 12 and a half. But the difference is here, that these isotopes exist in different concentrations in nature. And so carbon 12, if you recall, had a lot more percentage in nature than, say, carbon 11 and carbon 13 and carbon 14. And so when we sum and average out these 4 numbers, we take the fact that they are they're weighted averages, okay? Just like your grade is 10% for nomenclature, so on and so forth. So there's a lot more carbon 12 than there is 11, 13, or 14. So when we average out those numbers, we end up with 12.01 as the atomic weight, okay? Now, these numbers have units. Every atomic weight here has units, and those units are grams per mole, okay? So carbon has an atomic weight of 12.01 grams per mole. So what does that tell you? That means that if I take 12.01 grams in the lab and I weigh out 12.01 grams of carbon, guess what? I have 1 mole of carbon atoms. 1 mole of carbon atoms means I have 6.02 times 10 to the 23rd atoms of carbon. Now, if I go to, let's say, fluorine. Fluorine obviously has more protons, more neutrons, right? And it has an atomic weight of, a weighted average of 19. So if you were to weigh out 19 grams of fluorine atom, okay? I notice I said fluorine atom, just a single fluorine atom, it would weigh 19 grams. And I would have, guess what? 6.02, 1 mole, or 6.02 times 10 to the 23rd atoms of fluorine. Now, you know that fluorine is part of the diatomic molecule. There are 7 of them diatomic. So in real life, fluorine wouldn't exist as a single atom. It's a diatomic. And so I would have to double its atomic weight. So it would be, 38 grams per mole. But in either way, every atom here has an atomic weight. Phosphorus has 30.97 grams per mole. Its atomic weight. Again, I weigh out 30.97 grams of phosphorus, and I have 1 mole. Okay? 1 mole. Same with sulfur. Similar with sulfur. I weigh out 32.07 grams. I have 1 mole of sulfur atoms. 6.02 times 10 to the 23rd. Okay? All right. And it's analogous. And of course, you can have different weights, right? Because the different atoms, the carbon is much smaller than the fluorine. Fluorine's got more protons, okay? More neutrons, so it's going to weigh more. But I still have 1 mole of it, right? Just like your small, medium, large eggs. For argument's sake, the small eggs weigh, let's say, 100 grams per dozen. Large eggs maybe weigh 500 grams per dozen, right? I still have a dozen. If I get a dozen small and a dozen large, I still got 12. And obviously the small eggs are going to weigh 100 grams compared to the large eggs, which weigh 500 grams because they're simply bigger. But in both cases, I have a dozen, which means I have 12. Okay. All right. So this concept, pretty old concept. Let me show you this character here. Mr. Scientist Avogadro, there's a picture of him, interesting looking character. Okay, we have what's called Avogadros number. Okay, Avogadros number has the symbol N and then subscript A, capital A, which represents the symbol for Avogadros number. And it is 6.02 times 10 to the 23rd units. It's just a very big number, okay? Of anything, of whatever you want to count, just like a dozen. A dozen is simply nothing more than 12. Unless it's a baker's dozen, then you got 13, right? Okay. Now, let's give you an idea of how big this number is. Well, here's Avogadro number written here in the yellow box with, taking out a scientific notation, which reminds me, refresh your memory on how to use scientific notation on your calculator. Okay, remember we went through that exercise way back when, where you either have a button which is double E, okay, or you have a button that's listed as EXP, or you have in the newer calculators a button that's lists X and then 10 to the X, okay? So one of those three buttons you have. And then the other button to be aware of is the button for maybe, no, you don't need the positive, negative. It's all going to be positive numbers, okay? So that, fresh your memory how to use scientific notation, because you're going to be doing scientific notation on these big numbers. So if you take Avogadro's number and you put it in longhand, okay, this equates to 602.6 trillion. Okay, now if you were to give you a perspective on how large this number is, if you were to count, say, one particle, one number per second, 1, 1001, 2, 1002, 3, 1000, etc., 1 second, okay, it would take you roughly 19 quadrillion years to get to the end of that number. Okay, you'll be a fossil big time. So that's a big number. Here's 6 trillion right here. Give you an idea how big Avogadro's number. A billion has 9 zeros, trillion has 12. You've got quadrillion, and so this gives you a lot more perspective as how big, all the way to a Googleplex, which is a Google of zeros, which is a big number, okay? Humongous number. All right, so that gives you an idea about how big that number is. So if you had softballs, 1 mole of softballs, I don't know, a little bit larger than the baseball, I don't know, maybe 3 or 4 inches in diameter, okay? And you had 1 mole of that, guess what? You will have something that'd be the size of the Earth, okay? And the other aspect is this. That gives you hopefully a perspective as to the size of these atoms. Because if we measure out 1 mole of carbon atoms, that would weigh out 12.01 grams, okay? We have 1 mole and 12 grams. 12 grams is not very much, but the number of atoms of carbon is just astronomical for 1 mole. And sodium, if you weigh out 22.99 grams of sodium, okay, it has 1 mole. Now, something else to kind of hopefully maybe mess with your mind a little bit. Okay, water, H2O. We're going to talk about how to get the molar mass in this, but basically is this. We add up the atomic weight of all the atoms, okay? Oxygen 16, and hydrogen, there's 2 hydrogens. That's 2.02, 1.01 for each one. And so water has an atomic molar mass of 18.0 to grams per mole. Okay. Now, the atomic weights, remember, this is a ratio that we can utilize. And you just remember how we did the units when we're doing conversion factors. 1 inch is equal to 2.54 centimeters. I told you you can write that ratio with either inch in the numerators or inch in the denominators. But the same thing here with respect to atomic weight or the molar mass. So I can write 18.02 grams per 1 mole as a fraction, or I can invert it. And so for water, this is for water. And which one I use depends on the units I'm looking for. Remember the whole exercise of the conversion factors, I said, is keep track of the units. You follow the units, you got the problem set up properly. And so when I want, if I'm given moles is the problem, and I want to get the grams, obviously I want grams in the numerator, moles down in the denominator, okay? And the same token, if I'm given grams and I want to get moles, I use the one on the right. That conversion factor. And that's how we're going to be able to get from point A to point B by the atomic weights and the mole ratios of the balanced chemical equations. Okay. All right. So 18.0 grams per mole, which means that in 18.02 grams of water, 18 grams, we have 6.02 times 10 to the 23rd molecules of water. If you weigh out 18.02 grams, which is not a lot, it's roughly about 18 cc's or 18 milliliters, very small amount. And yet we have in there 6.02 times 10 to the 23rd atoms. That gives you a perspective as to how tiny these molecules of water are. I shouldn't say atoms, molecules of water. Okay. And that's just 18 grams. Now imagine for a moment if you knew how much water was in your body. That puts a perspective as to how many molecules of water are in your body. And then, go one more step. Think about all the water on Earth. Okay. And then convert that to the molecules. That number is astronomical. Astronomical, it's just mind-boggling. That's the number of molecules that are out there in nature, but just water. And I'm not even including all the other ones. So atoms are very, very small, extremely small. I was wanting to ask the question as to, well, do we have a picture of an atom? And my answer to that is we do have an image. Back in the 80s, IBM, in fact, came up with an instrument called, the initials are STM for scanning tunneling microscopy. Basically, it was a stylus, just like the old-fashioned record players. It was a stylus that scanned across your material, and it would get an image of whatever scanning. So they took things like gold metals and polymers, and they actually were able to get an image, and you get round circular images that represented the atoms. The resolution, probably I have not checked on that lately, but the resolution probably has increased and got a little better, but the initial pictures were like looking at a telescopic picture of we're looking at the moon, you can see the three-dimensional aspect, but it's kind of out of focus because the resolution is not that good. So yes, we've got images of atoms, and there are around, at least the images that we have, and we also got images of polymers, but they're very tiny, very, very tiny. Okay, so as I stated, that the mole is nothing more than a count. It's a number, it's entities, units, whatever you want it to be. But being in chemistry, we're going to talk about with respect to atoms or ions or molecules or formula units, okay? Now, recall that we had, let's say sodium chloride. Sodium chloride, based on the solubility rules, is very soluble, okay? And so it would dissociate in water to give us the sodium ion and the chloride ion. Now, notice there's no number in front of sodium chloride. It's understood to be a 1. Okay, so one molecule of sodium chloride will dissociate to give you one molecule of sodium ion and one molecule of chloride ion. Now, using the term molecule, but now I can change the word to say 1 mole of sodium chloride. If I had 1 mole of sodium chloride and I dump it in water, the ions dissociate and I get 1 mole of sodium ions and 1 mole of the chloride ions. Okay, now I take it one step further. If I have 1 mole of sodium chloride, do I not have 6.02 times 10 to the 23rd molecules of sodium chloride? Yes. And if I put them in water to dissociate, I would also get 6.02 times 10 to the 23rd atoms of sodium ions, and 6.02 times 10 to the 23rd ions of chloride ions. Okay, now that is kind of difficult sometimes to soak it through. Okay, because it's the big numbers here, right? All right, well, what if, let me put it to you this way. All right, I'm going to do a crude picture of a bicycle. Okay, so I'm not an artist, so this is a bicycle. All right. All right, so obviously if I have one bicycle with the frame and the wheels, if I take the tires apart, do I not have one frame? Right? Everybody agree on that, right? And do I not have 2 tires? Right? 2 tires. Okay. If I have 1,000 bicycles and I took the tires off all the bicycles, do I not have 1,000 frames? And how many tires would I have? 2,000 tires, right? And this is a bicycle. But let's do this. To keep it intact with the sodium chloride, let's, instead of a bicycle, let's make a unicycle. Okay, so if I have a unicycle with the frame and the tire, and I have one, I'm going to have one frame. Oh, let me fix my frame here. Get rid of that guy. That's supposed to be a unicycle. Crazy. Don't I not have one frame and one tire, just like down here, sodium chloride? So that means if I have 6.02 times 10 to the 23rd unicycles, and I took the tires off each and every one of them, I'm going to have 6.02 times 10 to the 23rd frames, right? And 6.02 times 10 to the 23rd tires, because I've separated them, okay? No different than down here with respect to sodium chloride. And you notice earlier I had the bicycle and I ended up with 2 tires. Well, you know, I could take barium chloride, dissociate that, and I end up with the barium ion plus 2 chlorides. That's analogous to the bicycle. I end up with 2 tires. The chlorides represent the bicycle. And so if I have 1 mole of barium chloride, I will have 1 mole of barium ion and 2 moles of the chloride ion. Okay. All right. So if you're ever asked about how many grams in 1 mole, okay, we simply just go to how many grams in 1 mole of the element, simply go through the element, and its atomic weight. Now notice I'm going to reuse, when I talk about the single element, I talk about the atomic weight, okay? When I talk about a molecule, a compound, I talk about the molar mass. Because with the atomic weight, this is one element, that's it. But with the molar mass, that deals with a compound. And I gotta add up the molar mass of all the atoms in that compound. And when I tally that up, that is the molar mass for that particular compound, like I just did with water. Water consists of 2 hydrogens and 1 oxygen. Oxygen brings in 16 grams per mole. Each hydrogen brings in 1.01 grams per mole. There's 2 of them, so I have a total of 18.02 grams per mole for the molar mass of water. Okay. All right, so when we talk about individual atoms, carbon, obviously, we talked at length about this. It weighs, its atomic mass is 12.01 grams per mole. Okay. Gold, obviously, is a much bigger element, much bigger. It has an atomic weight of 196.97 grams per mole, whereas sodium has an atomic weight of 22.9 grams per mole. And so if I weigh out these relative amounts, those amounts respectively, 12.01, 196.97, 22.99 grams of each respective element, I will have exactly 1 mole of that material, which represents exactly 6.02 times 10 to the 23rd atoms. Okay. All right. You know, it'll be analogous to, you know, small eggs here. This would be the small, the medium, and the large eggs. Okay, as an analogy would be. And the small eggs would be, you know, 12.01 grams per dozen. Okay, the large eggs would be 196.97 grams per dozen. And the medium eggs would be 22.99 grams per dozen. In all cases here, I have 12 eggs of each one. And obviously they're going to weigh differently, okay, per dozen. Okay. So basically, in a nutshell, the mole is the chemist's dozen. That's our dozen. It just happens to be a very large number. All right, so when we get to what's the molar mass, we need to determine the molar mass. Well, they will give you the name of the compound. And here's where your nomenclature comes into play, because from the name, we need to figure out the formula, because from the formula, we figure out how many atoms of each we have, which then, based on the atomic weight of each atom, gives us the molar mass. Now, why would we need this? Because, I'll tell you here in a second. Well, the first thing we're going to do is write the correct formula, okay? And we're given the compound right here, okay? Always write it in ionic form first, so you can make sure you put them together in the correct ratio. Once you, if you do that system continuously, you eventually will start to recognize just by the name what the formula will be. But until such time, write the ions first. Barium is a group 2A metal. So when it becomes ionic, it will have a +2 charge. So barium is a +2 charge. The hydroxide, hopefully by now, should send you to the polyatomic ion table. Okay, and hydroxide has the general formula of OH negative. Remember, the hydroxide stays intact. I did have students in the past, if we needed more than one hydroxide, that they will put a 2 down there. No, don't do that. Don't do that. And a -2, that is not 2 hydroxides. You don't change the subscripts. That's what they are right there. You need more than 2, you put parentheses. All right, so here, to put these together, you can see that we need 2 hydroxides for every barium ion. And we need that because we need to put them together such that we have enough cations and enough anions to balance, to cancel each other out. All right, so this 2 becomes the subscript in the parentheses. So we got B, A, parentheses, OH, subscript 2. That tells you you have 2 hydroxides, okay? Now we do a grocery list of all the atoms. And so we got barium here, okay? Very quickly, 137, yeah. 137.33 grams per mole. That is atomic weight of barium. Where did I get this number? Straight from the periodic table. Use our periodic table, okay? Because it has the correct sig figs. No, I don't want to use the sig fig term. Remember, yet we don't use the atomic weights to determine whether our sig figs are correct, because remember that these atomic weights come from whole numbers. It's the weighted average of the whole numbers, which tells you that they have an infinite number of sig figs, okay? So, but do use our sig figs because the answers to these calculations are based on the atomic weights given to you on the periodic table that I issued. All right, so oxygen, oxygen is 16, right? And there's 2 of them, so we got 32.00. Okay, grams per mole. And then we have hydrogen, there's 2 of them, so that's 2.02 grams per mole. Notice the units, grams per mole, go carry through, those are our total units, all right? And let me see, we got 3, so we're looking at 5, 3, 7, 8, 9, 10, 11, 6, 7, 171. Check my math. 171.35 grams per mole. That is the molar mass for the compound barium hydroxide. Clear it up and get rid of my mass. We calculated, but determine what the correct formula is. And you have to write the right formula because now to figure out the molar mass, you got to make sure you have the right number of atoms of each thing, okay? And so now you end up with 171.35 grams. Think about this for a moment. If you were in the lab and for whatever reason you weigh out 171.35 grams of barium hydroxide, you have 1 mole. 1 mole represents 6.02 times 10 to the 23rd atoms or molecules of barium hydroxide. Here's the other thing that we're going to talk about, and I'm going to introduce you. Notice something here. We have the total weight, right? The total mass of all the atoms. But we also have the individual contribution that each atom brought to the total mass. And so if you were to take the 137.33 and divide it by the total mass, and you multiply that by 100, guess what? You get the percent barium. And if I take 32, which is the oxygen here, divide that by 131.35, multiply that by 100, guess what? You get the percent oxygen. And the 2.02 divided by the total mass, total molar mass, times 100, gives you the percentage of hydrogen. Okay, all that should add up to 100%. Okay, that is the percentage for barium hydroxide, the percentage of barium in barium hydroxide. Whether that barium hydroxide came from here in the States or it came from tunnels for the moon, okay, that is the ratio. And we utilize this ratio every time in chemistry we make a compound. We have an idea of what it is, we clean it up, we calculate like I just did of what we think that compound is. We determine the percentage percentage carbon, percentage hydrogen, oxygen, nitrogen, sulfur, whatever else you think is in there. You shoot that off to the lab, they'll do an analysis, they send you back the number. You compare the percentage with what you calculated, and then based with all the other data you have pertaining to that compound you made, that just verifies that, yes, I made this particular compound, okay, based on the percentage. Okay, so remember that the units for atomic weight, molar mass, are grams per mole, grams per mole. Okay. Avocados number, again, is nothing more than a ratio, like everything else we've been talking about. And that being the case, we can write it in one or two ways, whether either with Avocados number in the numerator, as written here on the left, or in the denominator. Which one we use is relative, dependent on the question being asked, okay? Just like we did the conversion factors in, I think, chapter 2? Okay, when we're doing chapter 2 and 3. All right, so here the question is, how many calcium atoms are in 0.25 moles of calcium? Okay, like, so it looks very confusing here, but it's no different than when we were calculating, how many inches are in 2.52 centimeters. Okay. What do? We write down what we're given, right? We're given 0.250 moles of calcium, okay? And then write down what we're looking for. We are looking for atoms, calcium, okay? Those are the units we're looking for, atoms. And we're starting off with moles. So obviously we're going to have a factor here where we want to get rid of moles. So moles has to be in the denominator, right? I'm following through here, checking my units. And I want atoms in the numerator. Why? Because that's what I'm being asked to calculate. All right. And then I look for a conversion factor that has the units atoms over mole. And guess what? Right there. Atoms or molecules or bananas or oranges or whatever you want it to be is right there. And so it's 6.02 times 10 to the 23rd over 1. Okay. My moles cancel, leaving me with atoms. But if you think about it, you start off at 0.25, that's roughly approximately, and that approximately it is, it's a quarter of a mole. Okay, so that number that you're going to get is going to be less than 6.02 times 10 to the 23rd, which is good because it's a quarter of 6.02 times 10 to the 23rd. All right, let me clear this up and put in the better drawing here. Okay, here we go. Moles cancel. Leaving me with atoms, which is what I want. So this is where you're going to refresh your memory on using your scientific notation on your calculator, okay? And at 1.51, obviously it's a number smaller than 6.02. So yes, that number makes sense because of the mathematics that you did here. All right, now the next one. Calculate the moles of 3.75 times 10 to the 27 molecules of oxygen gas. Okay. All right. So let's write down what we're given. No different than the other problems we did with respect to conversion. 3.75 times 10 to the 27 molecules of O2, okay, and we're looking for moles. So we're looking for moles of O2. Okay, so what do we need to do? We need to put molecules in the denominator and moles in the numerator. Okay, moles in the numerator, guess what? We're using that one. 1 mole on top, 6.02 times 10 to the 23rd molecules. They cancel out, leaving us with moles of oxygen. Oxygen gas. So let me clear it up. So doing that, we end up with 6,230 moles of oxygen. Okay. Now, once you know moles of oxygen, because once you know moles of whatever you're looking for, the next logical step, if you think about it, is going to grams. Because guess what? When you're in the lab, if we were doing a lab here for real, your balance doesn't measure in moles, it measures in grams. Okay. Well, at least the ones in ours, and it could be pounds, whatever, but we use the metric system, so it measures in grams. So the next step is to convert that moles, guess what, into grams. Okay. Now remember the molar mass. The molar mass has the units of grams per mole, grams per mole. And the connection here, again, is the unit moles. So once I have my new ratio, which is the molar mass of O2, and let's figure that out real quick. The molar mass of O2, there's two oxygens, each one 16, so it's 32 grams per mole, right, for O2. Notice the key here is the term gas. When you see in the word problems, they talking about gas, then obviously you hopefully know by now that it's gas means oxygen gas. We know that that is the normal format structure for oxygen gas is diatomic, okay? Diatomic, so the formula would be equal to, if we would have said an oxygen atom, then obviously we're only dealing with 1/16. But this is gas, which should tell you diatomic. All right, so if I want to calculate how many grams that corresponds to, I'd go one more step and take what I got here, 6,230 moles of O2. Okay, obviously I need a conversion factor with grams in the numerator, moles in the bottom, and that is my atomic weight here, or molar mass, and that's 32 grams divided by 1 mole. Check my units, moles cancel, and guess what? Now, once I'll let you do the math, now I went from having a number of molecules of oxygen gas to moles of oxygen gas, and now to grams of oxygen gas, which then I can use in the real world because I'm using grams. We're going to take another step in a bit where we're going to talk about taking that same information and converting that to volume. Okay, because gases occupy a certain volume. 1 mole of a gas occupies a certain volume under certain conditions. So we can take this information and actually use volume as a measurement tool, given that we are under the conditions that we need to be. Okay. But throughout this, what I just spoke about, what is the factor that gets us from point A to point B is the mole. Okay. I got to get eventually 2 moles of something to get from point A to point B. Clear as mud so far? Okay. What we're doing here is we are going grams to moles, okay, mole calculations. Because remember, the atomic weight and the molar mass has the units of grams per mole, which is a ratio. We can write as grams per mole or moles per gram. Which one we need or we utilize depends on the question and what we're searching for, okay? So think about this now. Take one more step. if the molar mass is either written as grams per mole or moles per grams, we should be able to do calculations. If we start with moles, I can move to grams. And guess what? If we start with grams, I can move back to moles. Back and forth, okay? Back and forth. Now here it's asking you, how many grams is 1.667 moles of oxygen gas? Okay, how many grams? So let's write down what we're given and what we know. We are talking about oxygen gas. So again, like we did earlier, 32.00 grams per mole. Maybe we need that. I don't know, maybe we do. Okay, now, you know, I'm writing down what I know, what I do know. So I also know Avocados number, and I write that down, which is, I don't know, units per mole. I may or may not need to use that. That's okay, but I got it there for my sake in case I need it. So it's Avocados number and the molar mass, which I just denote as molar mass. All right, so, and then we get good old fashioned Na, Avogadro. So question says, how many grams? So obviously we're looking for grams of oxygen gas of O2. Okay, that's what we're looking for. We are given 1.667 moles of oxygen. Okay, so that's my first time I'm doing this one. I'm going to write down the units of what I'm trying to get to, and then I can look for conversion factors that will help me with where I need to get to finally. So I need to get rid of moles, so that's going to go to the numerator, okay? But the problem says I want grams, so that's going to go on top. So I need something that has the units of grams per mole, right? Obviously, Avocados number here wouldn't work because they're talking about units per mole, but the molar mass would, right? 32 grams per mole, so I can utilize that. My units cancel out. Now the question is, what's left is for you. You punch those numbers out. I can't control that part. But one thing is this, these moles, we're dealing with measurements, okay? Grams to moles, moles to grams are measurements, okay? So measurements have a degree of uncertainty. Therefore, they will be a factor in determining sig figs. Avocados number and Avocados number is a whole number, okay? 6.02 times 10 to the 23rd. So that wouldn't be a factor in sig figs, nor would molar masses, atomic weights, okay? And so your sig figs are determined by your measurement, which is 1.667, which has 4 sig figs, okay? So your answers should have 4 sig figs. All right, so here we go. Check the units out, it cancels out. So 1.667 moles of oxygen corresponds to 53.34 grams of oxygen gas. And the key part is oxygen gas, which is diatomic, which means you're using 2 oxygens. It's molar mass, okay? If you only use 16, then your answer would be half of that, and that would be incorrect because the word problem says oxygen gas and not oxygen atom. And how do you know it's diatomic? Because there's only 7 species that are diatomic. Have no fear of ice cold beverage. Remember that? If not, you may want to go back and review them. Okay, we have here how many moles is 45 grams of silver. So you went to the lab, you weighed out 45 grams of silver. Okay, so I think it's 107. Atomic weight of silver is 107.87. Yeah, 87 grams per mole. No, I don't have all atomic weights memorized. Okay. And I may need that. Would I need Avocados number? Possibly. No, not at all, because I need to go from moles to grams. Nothing here about atoms in here, so I don't need Avocados number. Okay, so but I'm always aware of it, depending on the question. All right, write down what you're given, 45 grams of silver. And obviously we have a conversion factor here, and we need to get to moles of silver. Okay. Keep track of your sig figs. You got 2 sig figs here with 45. And so we need grams in the denominator and moles in the numerator. Okay, which then means that we can use the molar atomic weight. So that's 107.87 in the numerator and 1 in the, in the denominator and 1 in the numerator. Okay. Now you plug it in, get your numbers, and it should come up to 0.42 moles of silver. Okay, so 45 grams with 2 sig figs divided by 107.87 gives you 0.42 moles of silver. Here's something maybe you can see a trend here. Think about this for a moment. If I start with grams, like I did right here, what did I do mathematically? I divided by, I would say, molar mass or atomic weight, okay? Depending on what you did, to give you moles or whatever, okay? If you start with grams and you need to go to moles, you divide by the atomic weight / molar mass. Guess what? What if you got moles and you want to get to grams? We do the opposite. You multiply by the molar mass / atomic weight. Okay? Look at your units. You see how they cancel out. But this is another way to help you remember. But I think if you keep track of your units, you don't have to remember, do I divide or do I multiply? Because that could be confusing and ambiguous at times. But if you keep track of your units, you have no question. You got it. Okay. Okay. How many grams is 0.554 moles of water? Moles of water. So we're still dealing with grams per mole, moles to grams. And so Avogadro number is not a factor here, but molar mass would be. And we did that earlier, and that was 18.02 grams per mole. Okay, because the formula for water was H2O, 1 oxygen, 2 hydrogens, and that gives us a molar mass of 18.02 grams per mole. Okay, let's write down what we're given. 0.0554 moles of water and we're looking for grams of water. Okay, so moles in the denominator, grams in the numerator. Okay, because I want the moles to go away, and those units represent molar mass. So we tap in right in 1802 divided by 1. So we have moles multiplied by the atomic weight / molar mass. You got grams. Okay. All right. And so roughly just a little bit shy of 1 gram of water, 1 cc of water has 0.055 for moles of water. So 0.998 grams of water represent 0.0554 moles of water. Okay. All righty. I think I got one more. Okay. Now let's read the question carefully. Up to this point, I've been checking and asking, do I need Avocados number? Well, it depends on the question, okay? Let's figure out what we're being asked. All right, they want to know how many grams, we're talking about potassium. How many grams of potassium is 4.75 times 10 to the 16 atoms? Okay, and so let's think about it for a second. Here, we're going from atoms, and from atoms, we need to get to moles, and from moles, it would get us to grams, okay? And think about it, it's the opposite direction too. If we start with grams, I need to get to moles, and from moles, I can get to atoms, okay? So if I got atoms, probably Avocados number, more like definitely, Avocados number is going to be utilized in there, okay? And once I'm at moles, I need the grams, I'm going to need atomic weight or / molar mass to get the grams. So either direction, grams, moles, atoms, moles to grams, I'm going to need Avocados number and the atomic weight / molar mass. Here, we're using the atomic weight because we're only dealing with potassium, okay? All right, so let me clear this up a little bit. And so let's write down what we do know, what we're given, 6.02 times 10 to the 23rd atoms per mole, okay? And then potassium has 39.10 grams per mole. Okay, that is the atomic weight for potassium. Okay, that's the information, the units that I'm more likely going to need here. All right, so let's write down what we're given. We got 4.75 times 10 to the 16 atoms of potassium. And we need to get to grams of potassium, All right, so we're going to need two conversion factors here. The first one gets me from, remember I wrote earlier, I got atoms or unit atoms to moles, to grams. I got to get to moles, okay? That's my universal unit from going from apples to orange. I got to get to moles. So obviously we're using Avocados number, and that is 6.02 times 10 to the 23rd atoms in the denominator, because I want atoms to cancel, and that is 1 mole. And so if I stop the calculation at this point, I would end up with the units of moles per moles of potassium, okay? Which would be great if that's what the question asked for. But no, the question asked for grams of potassium. So that means I need one more conversion factor. And I got to get rid of moles of potassium, but I want grams of potassium. Grams over mole is the molar mass. So that's what, 39.10 for 1 mole. So keeping track of my units, checking to make sure things cancel out. I got everything set up. My final units are in grams. And so now it's up to you to do the math. Let me clear it up. And you end up with 3.06 times 10 to the -6 grams of potassium. Hopefully this should give you a lot more perspective as to the size of these atoms. Notice that's a big hefty number. 4.75 times 10 to the 16. It's a pretty big number, okay? But that represents, weight-wise, for potassium, only 3.09 times 10 to the -6 grams. most of the balances in the lab, at least the ones in Chem 130, can only go to 4 decimal points. So we could not even weigh that amount, the balances that we normally have in the lab. Pretty small. So that small weight amount has a vast number of atoms of potassium. Again, to help you with the perspective as to the size of these atoms. Okay. Okay, so the takeaway here from these calculations is we need to write this up. We start with atoms. We need to go to moles to get to grams. Okay, and I can go in both directions. All right, and let me write this a little bit better here. Okay, so atoms slash molecule slash whatever you want to count with, okay? Go to moles, and grams. Okay, let me excuse me. And so if you got atoms and we need to get to grams, we have to go through moles, okay? And that would be, Avocados number right here. And if we have moles and we need to get to grams, then we're going to need either the molar mass or the atomic weight of whatever species we're looking at, okay? We cannot bypass the moles. We got to go through moles. That is the common factor that these calculations have to go from point A to point B, okay? Point A to point B. And we'll have a flow chart here in the bit to kind of put everything together so you can use the flow chart to help you through the calculations. All right, so which brings us to the following concept. In the beginning, we talked about properties of solid, liquid, and gases, and we stated that the gases at the time had no set volume, okay? Now, we're going to find that that wasn't 100% true, but at that point, yes, it was a true statement. There are certain conditions, and when we get to the last chapter on gases, additional conditions where gases do have a set volume, we can actually calculate it. But one set of conditions is what we call STP, okay? Standard temperature and pressure, okay? Now, the standard temperature is at 0 degrees Celsius, and the standard pressure is at 1 atmosphere. But 1 atmosphere, okay? So at 0 degrees temperature, Celsius, and 1 atmosphere. Right now here, it's approximately 1 atmosphere, our atmosphere on here, atmospheric pressure. Yes, it changes, it fluctuates on a daily basis, and also fluctuates as a function of altitude. So the atmospheric pressure in, say, Denver, a little bit different than, say, here in Phoenix area, okay? So only, and I repeat, only under these conditions, the following is true. And this is only for gases. Okay? If the problem does not say STP or say 0 degrees or 1 atmosphere, you can't do any calculations. The answer is, I can't calculate it, not enough information. Okay, so only at STP and only for gases. That if we take these gases like hydrogen, fluorine, ammonia, xenon, methane, and if we take a mole of each gas, obviously, hopefully by now you know that when I have 1 mole of anything, okay, I have Avocados number, 6.02 times 10 to the 23rd. Granted, clear up the messed up here. Okay. Granted, each one of these gases has a different molar mass. It's a different species, okay? And we're talking about molar mass, we're talking about the diatomic. So hydrogen, there's 2. Its molar mass is 2.02 grams per mole. Fluorine, etc. Okay, ammonia obviously is not diatomic. Okay, you got to add up the nitrogen and 3 hydrogens, that's 17.04. Xenon, 131, etc. Okay, so at STP, okay, that's the molar mass, obviously. That's the number of molecules for 1 mole of each gas. They all occupy a volume of 22.4 liters per mole, only at STP, okay, at STP. And guess what? We have another ratio, okay, 22.4 liters per 1 mole, or invert it, 1 mole per 22.4 liters. Another ratio, another unit you can keep track of and do your calculations. And so now, earlier I said we went from atoms to moles to grams. Now for gases, we can go from atoms to moles to volume to figure out the volume of that particular gas. But only, I repeat, only when you're at STP, 0 degrees Celsius and 1 atmosphere. Okay, that's the conditions. And that relationship comes into play, 22.4 liters per mole. Okay, so that being the ratio, we can, you know what, I gotta, give me 5 minutes here. I gotta take care of something real quick. I'm being asked for some assistance, so bear with me for 5 minutes. Be right back. Okay, sorry about that. All right, so here, you're being told STP conditions, so you can use that ratio of 22.4 liters per mole. The question is what is the volume of 1.25 moles of argon gas at STP? Okay. And so like any other of the questions we've been using or attacking, we write down what we know, 1.25 moles of argon gas, right? And we are looking for the volume, which will be liters of argon gas, okay, at STP. And so obviously here we want moles in the denominator, liters in the numerator. Moles cancel out. That's 22.4 liters, okay? And checking my units, everything's good to go. My units, liters is left over, so now I got 1.25 times 22.4 liters. Now, a word about this. 22.4 liters, unlike the other conversion factors we had, is a measurement, okay? And being a measurement, it could be a factor in your sig fig. So be careful on some of the homework problems. They might be kind of wrong because you didn't take into account the fact that under these conditions, 22.4 liters is a measurement. And so in this case, it would be a factor as far as sig figs, but in this case, 1.25 has 3 sig figs and 22.4 is 3 sig figs. So obviously our answer would be 3 sig figs. But if this were, let's say, 1.250, then yes, the 22.4 would be a factor in determining your final sig figs, because this has 4 sig figs and 22.4 has 3. Okay. All right. So we set that up, and that means that 1.25 moles is equal to 28.0 liters, okay? And then ask yourself the question in all these calculations, does this number make sense? Okay, well, think about it. You were given 1.1, about 1.25 more moles. So it stands to reason that this number is going to be greater than 22.4 liters. And sure enough, you got 28, because you got 1/4 mole more than 1 mole. So that number makes sense. If this number was less than 22.4, given what you're given as a problem, that should send a flag out to say, that number doesn't look right. Let me check my math. Okay. All right. Next one here says, how many moles is 30.4 liters of oxygen gas at STP? All right. So we're looking for moles of O2 given 30.4 liters of O2. All right, so then we're still at STP, obviously. So we want liters in the bottom, moles on top. Okay, so that's 1 mole and 22.4 liters. Now look at the problem. You're starting off with 30.4. Okay, you know that 22.4 is 1 liter, so your answer is going to be greater than 1. Right? Makes sense, right? Should be greater than 1. If it's not, then something was set up incorrectly. All right. So that corresponds to 1.36 moles of oxygen, 30.4 liters. All right. Now, how about this one? This was a little more interesting. We're still at STP, so we could be still using liters per mole. Okay. And then here we're asking the mass. Well, when you're being asked a question for a mass, that will imply, it doesn't imply, it tells you, I need the molar mass. And we're talking about chlorine gas. So chlorine, as you know, is diatomic, right? And so each chlorine is 35.45? And so we need 35.45 times 2. So we got 10, 9, 10, 7, 70.9 grams per mole for the molar mass. Okay, so we got what we need. We need the molar mass. We need the relationship at STP at 22.4 liters per mole. We don't need Avocados number, but if they ask how many molecules that would be, yeah, we would need Avocados number. So we don't need that here. So let's write down what we're given: 4.50 liters of chlorine gas. What are we looking for? We will need to calculate the mass of chlorine gas at STP. All right, so we got liters here. And with the case I showed earlier, where I had atoms, I had to go through moles. Well, if you have liters to get any place else, you have to go through moles. So again, it emphasized that starting with atoms, molecules, units, or volume, okay, and I'm trying to get to grams, I have to go through moles. Okay, so I need a factor that puts me into the mole ratio. Not the mole ratio, but into the mole universe. So here we got 22.4 liters per mole. We want liters in the denominator, and guess what? Moles on top, okay? And so at this point, these units, liters cancel, leaving me with moles of chlorine, which would be great if the question were just asking for moles, but it's not. It's asking for the mass. It's in grams. So I got to go one more step, and that is grams in the numerator, moles in the bottom. And that is the molar mass. So I got 70.90, 1 mole. Check my units. Moles cancel out. Volume cancels out, leaving me with units of grams. So the problem has been set up properly. Okay. And now it's a matter of you doing the math. 4.50 divided by 22.4 multiplied by 70.9. Let's clear up my mess. And we'll put that in there. And there you go. So 14.2 grams per 4.5 liters of chlorine gas. Okay. Remind yourself, this is 4.5 is a volume measurement, 22.4 is a measurement, but they both have 3 sig figs. We don't use the sig figs for atomic mass, so our answer should be in 3 sig figs, 14.25. Again, I emphasize, if this was 4.500, then your answer would still be 14.2. Okay. All right. All right. Any questions at this point? Feel free to jump in there. All right. This flow chart breaks it down. We're going to have another flow chart, but this is for the topics that we just finished talking about. Notice here that the key is moles. Okay. You can't go from grams to atoms or vice versa, cannot, without going through moles, nor can you go from grams to volume without going through moles. And the same is true about atoms to volume, okay? Without going through moles. Moles is the common factor that connects everybody. Okay, it's the universal factor that connects bananas and oranges. All right, and so let me erase this. If I start off with grams, okay, I'm going to need molar mass or atomic weight, depending on what the material is, okay? But I'm going to interchange the term atomic weight, molar mass. You should know by now that if it's just the atom, that's the atomic weight. But I'll just call it molar mass, so there won't be no confusion. All right, so from the molar mass, we are going to, starting with grams, guess what? We are dividing by the molar mass to give us moles. Okay, check your units, you'll see that's what we do. Once, only and only when you are at STP, only at STP, can you go down in this direction, okay? Using the relationship of 22.4 liters per mole. And if they're asked to calculate how many molecules that is, X number of grams, then you're going to need Avocados number here to get me to the number of atoms, ions, molecules, formula units, whatever you are counting. Okay. Now we can go from the units. Here's the thing. Units can bring us. Let me change the color here real quick. Going from units, you can go to volume. Okay. Going from grams, you can go to volume and back. And every combination thereof, going from grams to atoms, back and forth, back and forth. But you got to go through moles. Can't do it without the moles. So this flow chart, when you're working through the problems, will greatly assist you to make sure you're setting it up properly, because if the problem gives you grams and you got to go to volume, then you know what you need to do. You need the molar mass, you need this relationship to get through that, okay? And you start setting up conversion factors back to back. We will eventually get to the point where we're going to set up at the minimum of at least 3 conversion factors when we start doing calculations and reactions, okay? All right. Here's an example. How many grams does 17.35 liters of neon gas mass at STP? And so they ask you, how I got 17.35 liters of neon gas and we're at STP, how much does it weigh is the question. And so we write down what we're given. I also wrote the answer there. So we're given 17.35 liters of gas, all right? And so we're at STP. And so I throw in the first, the relationship of 22.4 liters per mole, okay? Then we're talking about the neon gas, so I need to convert that to grams, so I need the molar mass, okay? 1 second, please, I gotta. Sorry, something made me sneeze. Okay, so 17.35 liters, okay, divided by 22.4 times 20.18, which is the molar mass of neon gas, gives me 15.6 grams. Now let me ask you a question. How many sig figs does 17.35 have? Anybody know that?
4.
Exactly. Now, how come does our answer have 3 sig figs?
One of them's a 0.
What's that?
One of the last number was a 0.
No. Yeah, we got, you're correct. This is 4 sig figs. This is 3 sig figs, is the answer. And we don't use the atomic weights, were not used. Okay. But recall what I said about 22.4?
Oh, it has the least amount of sig figs.
Yeah, because it's a measurement. And so, yes, the 22.4 could be a factor in the calculations with respect to sig figs. And here's an example where it is. Because you start off with 4, but you end up with 3, because the 22.4 determines the accuracy of your final answer, okay? Because it is the least accurate number. Okay, good. All right, and now, once you've been asked the second part of the question, well, how many atoms does this pertain to? All right, so same setup, we throw in the 17.35 liters. We're still at STP, so we need to convert that volume into moles. And then, except this time, we bring in Avocados number because they want to figure out how many atoms does 17.35 liters correspond to. So you plug it in, calculator, and you should come up with an answer of 4.66 times 10 to the 23rd, okay? To the 23rd. Atoms of neon gas has a volume of 17.35, okay? And yeah, has a volume of 17.35. And again, the same reason your answer should be in 3 sig figs because of the 22.4. So that is a large number of atoms actually, but relatively small volume. Okay. Any questions about these type of reactions? I mean, the takeaway here from this part is this flow chart. This flow chart puts it all together for you, okay? Follow the flow chart. But we're gonna have another flow chart that encompasses more information that you can utilize when you're doing the calculations, when we start working with the reactions and figuring out how many grams of product or how many grams of reactant we need, okay? But this is part of that one flow chart that we will give you. You'll see down the road. Okay, which brings us to a density. We did talk about density before. Density, again, is another ratio, which is the mass over volume, okay? Now, if we are at STP, we can simply calculate the density of a gas by taking mass, the molar mass, and dividing it by the molar volume, okay? And so, for example, it's asking you to calculate the density of ammonia gas at STP, okay? Well, all we need is the molar mass for ammonia, which is 1 nitrogen, 3 hydrogens, which corresponds to 17.04 grams per mole. And the molar volume at STP for all gases is 22.4 liters, okay? And that corresponds to 0.76 grams per mole, okay? Which are the units of density. And you might think, well, wait a minute, how did that happen? All right, let me change the color here just a little bit. We have grams per mole divided by liters per mole. Okay, so we are dividing by a fraction. Now what happens when we divide by a fraction? We invert the fraction and multiply through. So this becomes grams per mole times moles per liter. Okay, see how that? We inverted the fraction. It's like taking 1/2 divided by 1/5. Okay, that corresponds to 1/2 times 5/1, which is 5/2. Okay, that's what we're doing here. Notice the moles cancel unit-wise, leaving us with units of grams per liter. So at STP, we can simply calculate the density for any gas at STP only, okay? By just simply knowing the molar mass, and you know the molar mass by adding up the atomic weights of all the atoms in that compound. All right, which brings us finally to the percent composition. And what we're going to end up doing is we'll finish up this chapter. And then come next Friday, I'll do the spreadsheet, not the spreadsheet, the worksheet for this chapter. And then we'll jump into the next one, okay? And then, unless you got other questions, we're more than happy to jump into those. Now, I did talk about this here when we were talking about the percent composition earlier. You know, when we're looking up we're figuring out the molar mass. And then at that time, I say, hey, look, watch this carefully. I can take the amount that every atom brings to the overall molar mass and divide it by the total molar mass times 100, and you get a percentage. Well, that's where we're at. If, for example, you take water, we know that water has a molar mass of 18.02. I demonstrated that already. 1 oxygen, 2 hydrogens, okay? Every hydrogen brings in 2.02 grams based on its molar mass. Now, be careful, these units here, there's a typo. It should be grams per mole here. They said grams, that's incorrect. It's grams per mole, but it doesn't make a difference because they all cancel out. But I want to be technically correct, okay? The atomic weight is not units of grams, it's units of grams per mole. I'm going to fix that when I get done with this. So 2.02 divided by 18.02 times 100 says hydrogen represents 11.2%, okay? We do the same for the oxygen, excuse me, and it is 88.79% oxygen, which that should tally up to be a total of 100%. It might vary at 99.99, but you still, if you're not anything like that 99.99, you're like 60%, something went wrong, obviously, right? You should add up to 100%. So what that tells you, that water consists of 11.2% hydrogen and 88.79% oxygen. And that is true for water, like I stated, found here or found in the next universe or in the next, wherever, next star. It still has that same composition. Okay. So there is any questions about that part? Yeah. So with that, we can very quickly, I'll go through this very quickly. Let's find the percent composition for TNT. Anybody know what TNT is? A little side note here, very quickly.
Dynamite.
It is dynamite. Okay, there's another trivia question. Anybody know who discovered it? I'll give you a hint. There's a famous prize given out every year for the gentleman who discovered TNT. They give a prize in medicine, they give a prize in literature.
Nobel Peace Prize.
You got it. Nobel was the guy, which is kind of fascinating that he did this because to make this compound is tough to make, very explosive. Anyway, its general formula is C7H5NO2. There are two nitro groups, three of them, I should say, and it's called trinitrotoluene, hence TNT. Okay, you do the composition, we simply add up all the carbons. Okay, I always use the periodic table. We got 7 carbons, 12.01 for each carbon. Okay, we've got 5 hydrogens, each at 1.01. That's a total of 5.05. Then the nitrogens, there's 3 of them at 14.01. So that's a total of 42.04 grams per mole. Okay, so that gives us, oh, and the oxygens, of course, there's 6 of them. That's a total of 96. So we have a total molar mass for TNT of 227.15 grams per mole. Now, to figure out the percent composition, we simply just take the contribution of carbon, which is 84.07, divided by the total molar mass, times 100. That gives you a percentage of 37.01% for carbon, 2.22% for hydrogen, 18.5% for nitrogen, and 42.26% of oxygen. Okay, and so that's how we do a percent composition for any compound. As long as you got the formula, you can just figure out its molar mass and then divide through by the total contribution of every atom times 100, and that gives you the percent composition. Okay, don't forget to use the periodic tables. All right, you might try these at home. And in fact, if you have trouble with it to get those same answers, it's a good opportunity. Next Friday, we can bring them in and go over them. So how many liters is 3.425 grams of carbon dioxide gas? Okay, so that should be 1.74 liters. How many molecules are in 3.425 grams of carbon dioxide? You should come up with 4.68 times 10 to the 22nd molecules. And then finally, how many grams will 3.0 times 10 to the 15 molecules of carbon dioxide mass? How much would it weigh? Very small weight, 2.2 times 10 to the negative 7 grams. Okay. All right. Well, oh, I had a question here. Sorry, I didn't get the. Yeah. Yes, the question was because of the 22.4. All right. So try these at home, see if you can get that same answer. If not, we'll go over them next Friday. And that.
Thank you. Have a good weekend.
All right, guys. That ends it. Have a good weekend.
Thank you.
And,
I have a quick question about the extra credit. What lab beaker drawings are they from? I'm a bit confused on that.
oh, no. The extra credit was the nomenclature. Oh, no. Let me get my class correct. There was an extra credit for you there. And you had a question about the beaker diagram. Is that what you're asking?
But it's like a separate homework assignment. It says activity B, extra credit beaker drawings, chapter 9.
Yeah,
But the homework we just did you want us to like redraw them? I'm just unclear on what to do for
Yeah.
that.
exactly. Just submit. I'll let you choose how you want to handle that. You can submit what you drew for that homework or redraw. But it's, okay, I'll let
And-
you decide on that. Yes.
Was that the homework that was due today, or is that the homework that was due last week?
Now I have to check that. For the extra credit or just the homework?
For the extra credit that the homework is about.
Okay, give me 1 second here. And let's. Got logged out here. 1 second. Okay, and so today's April 1st, we got activity B, beaker drawings. That is the one that was due today for extra credit.
And
And
another
then,
chapter. Oh, sorry.
no, go ahead.
What was it for the lab chapter 9 or like the chapter 9 homework? Because for the homework, I didn't think we had it was just like the multiple choice questions, right?
Yeah, exactly. The homework, just the regular homework, nothing there. Yeah, there's nothing to submit just in your homework. The activity was simply, draw drawings and submit those. Okay. And then you have today, you have lab 8 today, and then lab 9 is not till next week.
Okay. So what do you want us to do for the extra credit assignment?
Oh, just simply draw. Let me pull it up. Okay, it had it there, when you go through there, okay, there are some questions, okay? And it depends on which one, because there's different questions and every student gets a different question. Okay, but so for example, if one question you may draw, it depends on when you access the exam. This is draw a beaker drawing for sugar, magnesium carbonate, and sodium carbonate. Okay,
Oh, okay. I see. Yeah, I see. So it tells us what we draw in the
yeah,
extra credit.
exactly.
Okay,
Yeah.
that's what I was confused about.
Okay, it tells you which one, and I don't know which one you would get. There's like, 8 or 9 different ones, and it depends on when you access that exam or that extra credit, which one is given to you.
Okay, that makes sense.
That makes sense? Yeah, okay. Good.
Okay, yeah, thank you.
Yeah, no problem.
All right, have a good day.
All right, you too. Thank you.
Of course.
Bye.
Bye.
You say bye-bye to everybody.
Thank you. Thank you, Dave.